To start with, let us apply these two binary operators that we just saw, plus and minus, on these two variables. For every variable x and y in a binary set B, then which means that the OR operation of x and y is also in the same set, and the AND operation of the two elements are also in the same set. Right? Now let us slowly apply different laws. Now, commutative law. What is commutative law? For every x and y in a binary set B, then x plus y will always be equal to y plus x. Quickly, let us verify this. If I have a set x and y, right? What is x plus y and y plus x? They will be same, right? So the different binary combinations for a two variable are 0, 0, 0, 1, 1, 0 and 1, 1. X plus y is nothing but an OR operation here. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1 and 1 plus 1 is 1. Similarly, y plus x is also an OR operation of y and x. So 0, 1, 1, 1. So these two Boolean expressions, they are equal. So that's what is commutative law tells you. X plus y is equal to y plus x. Similarly, the AND operation also. You convert this into AND operation, x dot y and y dot x. So it will be 0, 0, 0, 1, and here also it is 0, 0, 0, 1. Okay. So this is what is a commutative law. This associative law. If you have three variables x, y, z in a binary set, then what associative law says is x plus y, please remember this, x plus y plus z will be equal to x plus y plus z. Or in other words, they are also equal to x plus y plus z, which is true for an AND operation also. X and y and z will be equal to x and y and z will be equal to x and y and z. Now identities with zeros and ones. We have already seen this particular identities somewhere earlier also, especially when we were dealing with the NAND, NOR and XOR gates. If you recall, what is the NAND operation of 0 and any variable x? It was a complemented value. This was in the case of a NAND gate. Similarly, in case of a NOR gate, so this has to be 1. Similarly, in case of an OR gate, it was 0 dot x was a complement. Similarly, we saw it in case of an XOR gate also. So likewise, the identities with 0 and 1, always any number you OR with x, 0 is ORed with x, which is equal to, as per the commutative law, it is also equal to x plus 0, which will always be equal to x. Similarly, 1 dot x is x dot 1, which is always equal to x. Right? So what does this mean is, when you are ORing a variable with 0, then the resultant outcome will always depend on the variable's input only. If x is 1 here, your output will be 1. If x is 0, your output will also be 0, which means it is dependent on x. Similarly, for an AND operation of x with 1 and x, your output will always depend on x1. If 1 dot 0, then your output is 0. If 1 dot 1, then your output will be 1. Okay. Distributive law, you have already seen. For x, y, z, three variables in B, x dot y plus z will be equal to, you distribute and multiply, x dot y plus x dot z. Similarly, this is a new distributive law might be for you. X plus, we will be using this law, so please remember this particular law at least for time being. X plus y dot z is equal to x plus y dot x plus z. This can be well proved if you first solve the right hand side. So just to quickly prove this, you use distributive laws on the right hand side. So what you have is x dot x plus x dot z plus y dot x plus y dot z. right? So you can pull out x from all these things. So x, when you pull out, it will be x plus y plus z. So, or in other terms, the first term you can write this as what is x dot x. X dot x is nothing but if it is 0 dot 0, it will be 0. 1 means it is 1 dot 1, it is 1. So its value is going to be x. So this can be written as 1 plus z dot z plus y dot z. So this can be 1 plus anything. Just we saw the identity, right? 1 plus, here it is 0 plus. If it is 1 plus anything, then obviously this particular result will always be 1. So that is why this gets simplified to x plus y dot z. So from right hand side, we try to prove to the left hand side. So this you remember because we will be applying this in another identity right now towards the end of this page. Now the complement identity, what is a complement or an inverse identity is you are a variable and its complement, the output will always be 1. You AND the output and its complement, then the variable and its complement, it will always be 0. So the logical operators as mentioned here for the set B, if it is 0 and 1, and the logical operators OR and AND, they do not satisfy all axioms of Boolean algebra. Now, whenever you are having a complex Boolean expression, then the precedence is very important, right? So what is the precedence of operators that they carry is parenthesis which has the highest parity, the priority, and the complement will get the next priority, and operation will get the third priority, and OR operation will get the fourth priority. In case, say for example, you have A dot B plus C, then obviously the parenthesis part will be first executed. This carries the first priority. And then if you are having a bar here, the complement will get the second priority here. And the third priority, this AND operation will get the third priority. And if you have say some variable, say B plus this variable, then this plus will get the fourth priority, right? Now, what is a truth table? Truth table, this particular term we will come across till the end of this course. Truth table is a very important part. What is a truth table is? Truth table is a table that will list you all the possible input combination and its corresponding output combinations. Normally a truth table will contain the input side and the output side. Input, we will have all different possible input combinations. A very good example of a truth table is a truth table of any gate. You consider an AND gate here. So X and Y are the inputs, and if Z is the output, where Z is equal to X dot Y, what are the all possible input combinations? So 0, 0 is one input combination, 0, 1, 1, 0 and 1, 1. These are the different input combinations. And what its corresponding output combination? 0 dot 0, 0, 0, 0 and 1. Right? So this table here is called as the truth table. Now, just to tell you a proof of a truth table, say for example, you have an expression x plus y plus z is equal to x dot y plus z. This is nothing but a simple distributive law which we just studied here. X dot y plus z is equal to x dot y plus x dot z. Now, the truth table is the one that will help you to prove that the left hand side of your expression is equal to the right hand side of your expression. There are two ways by which you can prove these postulates or these idioms. Either you can use the truth table method or you can use the different rules of Boolean algebra. If we try to prove using truth table, then what is the expression we have? The expression we have here is, it is x dot y plus z must be equal to x dot y plus x dot z. This is what we need to prove. So how do we make a truth table? What are the variables here? We have x, y and z are the three variables. So we have here the three variables, which means instead of writing this as variables, we write it as input variables. All these are inputs, and which is the output? This particular table, and this particular table is what is your output is. Now let us, how do you complete this? What is y plus z? Please note it is not a arithmetic y plus z, it is a Boolean y plus z, which means that y and z are y or z. So what is 0 or 0? It is 0. 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. 0 or 0 is 0. 0 or 1 is 1. 1 and 1. Right. Now what we should do? We should find out x dot y or z, which means that the AND operation of this column and this column's AND operation. Okay. What is 0 and 0? This is nothing but 0. 0 and 1 is 1. 0 and 1 is 1. 0 and 1 is 1. Oh, I'm sorry. I got. Okay. So 0 and 0 is 0. 0 and 1 is 0. 0 and 1 is 0. 0. 1 dot 0 is 0. 1 dot 1 is 1. 1 dot 1 is 1. Right. And one more. 1 dot 1 is 1. Okay. So now let us come to the right hand side. The right hand side has got two expressions, x dot y and x dot z. What is x dot y? X dot y and operation of x and y. So this will be 0 dot 0 is 0, 0 dot 0 is 0, 0 dot 1 is 0 again, 0 dot 1 is again 0, 1 dot 0 is 0, 0, and here 1 dot 1 is 1 and 1. Right? Now let's look at x dot z. That is, you look at this x table, this column and this particular column. Now what is x dot z? It is 0. X dot 1, 0 dot 1 is 0. 0 dot 0, 0, 0, 0, 1 here, 0 here and 1 here. Now we have to perform OR operation of these two columns. This column and this column, we have to perform the OR operation. What is 0 plus 0? 0, 0, 0, 0 here, 0 here. 0 plus 1 is 1, 1 and 1. Now compare these two tables, this column and this column, both are same. So this is one way of proving your Boolean expressions. We are trying to prove that left hand side is equal to right hand side. This is one way of proving using truth table. Okay. So postulates can be proved even by truth table option also, or you can prove by applying the different rules of different idioms of these postulates. Now coming to the next concept called as a duality. You must have studied this concept of duality even in your introduction to electrical engineering course also. What do you mean by duality is, you must have studied something called as mesh analysis, right? And you must have studied some analysis called as nodal analysis. Your mesh analysis and nodal analysis are dual applications, duality applications. What do you mean by that is, if you have a circuit like this with three meshes here, then this circuit can be transformed into an equivalent nodal analysis circuit with three nodes. Right? This circuit and this circuit, they will be equivalent by the concept of duality. Similarly, in Boolean algebra also, the duality principle is very, very powerful. Now, what is this particular duality is, in any expression, you can always interchange your operators and your elements also. That is, you can interchange your binary operators and at the same time your identity elements. What do you mean by that? Is you can transform plus to dot and 0 to 1, and similarly dot can be transformed to plus and 1 can be transformed to 0, and this principle is called as a duality principle. We will see an example here. If say for example I have an expression a plus b dot c is equal to, by applying the distributive theorem, what is this equivalent to? This is equivalent to a plus b dot a plus c. There is a mistake. A plus b dot a plus c, because when I apply the distributive rule, it is a plus b dot a plus c. Now, what is the duality theorem says? You transform plus to dot and dot to plus. You transform 0 to 1 and 1 to 0. So here, if we transform this plus here to dot and this dot to plus, then on the right hand side also, this plus gets transformed to this dot and this dot gets transformed to plus. This plus will get transformed to this dot. Okay, so this is how both the expressions are equivalent. In fact, these two expressions are equivalent. Okay, so what it says is, if one of them is true, then the other will also be true. The dual equation will also be true. So hence, why are we doing this duality? Why are we doing this duality is, it is okay to prove one of the expression and you can apply the duality principle on the other, and you can say that hence this is also true. Okay, so that is the advantage of applying the duality principle here. And let us see more example of a duality here. If say for example x plus y plus z bar, the whole bar is equal to x bar dot y bar plus z. Please note that if this is true, only then the duality is true. What is the duality will say? Change this plus to dot. Change this plus to dot, this y to dot here, and similarly this y dot convert to plus, this dot convert to plus, then then these two expressions will also be valid. Please note, only if the above expression is true. Only if this expression is true. If this expression is false, then obviously the duality expression that you apply will also be false. Okay. Now let us apply a very simple rule. We have just studied that ORing a variable with 1 will always be equal to 1. Right. So obviously this is a valid expression. So what is the duality of this expression? X plus gets converted to dot and 1 gets converted to 0 will be equal to 0. Right. Obviously this is true, right? And operation of a 0 with any variable will always be 0. Right. So this is also true. Now I am going to introduce you about two important terms in Boolean algebra. Say for example, what is that? The first is called as the tautology. What do you mean by tautology here is, if you have an expression and if the output of that particular expression is always 1, then those kind of expressions are called as a tautology expression. Similarly, if the output of the Boolean expression is always false, then those kind of expressions are called as fallacy expressions. Okay, an example of a tautology expression is, here it is given, P plus PQ bar is a tautology expression. How can I prove? What is that? P plus PQ bar. Now you put, what are the, since P and Q are two variables here, if I create a truth table and let me call this expression as some z and the output z here. So the four different possible input combinations, four possible input combinations are 0, 0, 0, 1, 1, 0 and 1, 1. So what will be the output here? If P is 1, whenever P is 1, right? So this is an OR operation only, right? So your output will always be 1. So where is P is 1? P is 1 here. So your output is 1. Now whenever Q is 0, this output is 1. Why? Because Q bar is 1. So 1 dot, yeah. So if, okay, so 0, this is not a tautology expression then. So P plus PQ bar, if Q bar is, if P is 0, so let us apply the first one. So this is 0 plus, I think P plus Q bar, I believe. Yeah. Yeah. P plus Q bar will be a tautology expression. So if P is 0, then this is 0. Q bar is 0 means this is 1. So this is going to be 1. But then this doesn't get applied here, right? Okay. So I'll give you a different example of a tautology expression. This expression is not a tautology expression because your output has to be 1 always. So what we can do is P plus.
So we can say P plus P bar.
Yeah, P plus P bar is obviously. I want to give an example with 2 variables. Okay, fine. I think I will come across an expression. I'll tell you that time. Okay. Now, next is some of the basic theorems of Boolean algebra. I'll give you a different example of a fallacy and a tautology expression. Maybe you can get in the exam also. Okay. Now, what is an idempotency? If x plus x is, then your output will be equal to x. Similarly, if x dot x is equal to x, how can you prove this? X plus x, this can be written as x plus x, you multiply it with dot. It doesn't change, right? By identity rule. Similarly, you apply a distributive property here. Right? This 1 can be written here. This 1 can be written as x plus x bar. X plus x bar is always 1. Right? So now you apply distributive law. X dot x is still x. X dot x bar plus, okay, let me expand this. X dot x plus x dot x bar plus x dot x plus one more x dot x bar, right? So obviously x dot x plus x dot x will always be equal to x dot x. Similarly, x dot x bar plus x dot x bar will always be equal to x dot x bar, right? Don't apply arithmetic operation. Don't write 2 times x dot x, okay? Because here it is something like 1 or 1, right? So this 1 plus this 1 will always be equal to 1, right? Similarly here also. Now what is x dot x? X dot x is nothing but x plus x dot x bar. And what is the complement of x dot x bar? X dot x bar, this particular term will always be equal to 0, right? So x dot x bar here will always be equal to 0. So x plus 0 is x. So thus we have proved x plus x is equal to x. Likewise, you can prove x dot x also equal to x. Now let's move on to further theorems. X plus 1 is equal to 1. You can apply the duality principle to it. X dot 0 is 0. Complement of a complement is x. Please note here that we will be using this very often when you are trying to implement a complex circuit into a NAND only circuit or a NOR only circuit. Then the absorption rule, x plus xy equal to x, and x dot x plus y is also equal to x. So if you want, we will prove this one. X plus xy, you just multiply this particular part with 1, x dot 1 plus x plus y. You apply the distributive rule, pull out x common here, then it will be 1 plus y. 1 plus anything is always 1. So x dot 1 is nothing but x. Okay. Now this you can apply the duality principle here. So x multiplied by x plus y, you can write it as, you can distribute and multiply. It will be x dot x plus x dot y, and then which is nothing but x plus y, because x dot x is also x. So you pull out x common, so it will be 1 plus y, 1 plus anything is 1, so it is x. So x multiplied x and x plus y is always x. Now the RLR rule, redundant literal rule. What is that says is, it is x plus x bar dot y is x plus y. Just I'll give you a proof of this. You have just studied this rule, right? X plus yz equal to x plus y into x plus z. I asked you to just remember, right? So this is nothing but a distributive law. This is nothing but a distributive law. Now from this you multiply, you separate this x as x plus x bar, this particular expression here. X plus x bar is nothing but 1, right? So 1 can be written as x plus x bar multiplied by x plus y. This is nothing but 1 here, so it is x plus y. So you can apply the same rule here. Instead, the only difference here is z is equal to 1 here. We are applying this particular rule provided z is equal to 1. Okay. Now coming to the De Morgan's rule. Again, we have already seen multiple times, break the line and change the sign. X plus y the whole bar, x plus y the whole bar is equal to, if you break the line, then it becomes x bar and plus will change to dot and y bar. Break the line and change the sign. Similarly, if you have xy the whole bar, when I break the line, it will become x bar and y bar, and I have to change the sign also. Dot gets changed to plus. What is this? This is nothing but a NAND circuit. And what is this? This is nothing but a OR circuit, but a complemented OR circuit. This is not OR, but a complemented OR. We will see this theorem now. Then a consensus theorem. What consensus theorem says is, that is, you have to apply the consensus theorem. AB plus A bar C plus BC is equal to AB plus A bar C. This is what you need to remember. If you come across 3 variables, AB plus BC and complemented form with A bar and C, right? Now this can be written as, BC can be written as BC dot 1. 1 can be written as A plus A bar. Then you cross multiply, you apply distributive law. Then it will become ABC plus A bar BC. And now what you have is, you combine AB here, ABC here, you pull out AB common from this. Here you have A bar C, you have A bar BC, you pull out A bar C common, you will have common as A plus B. 1 plus anything is 1, 1 plus B is also 1. So this becomes AB plus A bar C. So what is the consensus theorem? Consensus theorem is AB plus BC, right? And then the complement of A and C is equal to AB, the first term, and the last term, A bar C. This particular term vanishes. This you must remember. Next is one more consensus theorem. Just we saw this consensus theorem, but in terms of ABC. We just saw this. The duality is also true. What is the duality of this? Maybe we can write the duality expression for this. What is the duality expression for this? This will become, for duality we have to change the sign as well as 0 to 1 and 1 to 0, right? So here also you can apply the same thing here. Let us change the sign first. A dot B becomes A plus B plus B plus C I'm sorry, this plus will not be there. Instead, this is a dot and then dot a bar plus c will be equal to a plus b dot a bar plus c, right? So the duality also is valid. So that's what is mentioned here, the consensus theorem. X plus y, that is I have applied the duality for this. Dot becomes plus, this plus becomes dot, dot becomes plus, and so on, right? So this is called as the consensus theorem, and maybe the proof of the second consensus theorem you can do it on your own. Now let's move on to the Boolean functions. Boolean functions. Now, if you look at the way we are treating the algebra, Boolean algebra, it will be very similar to your linear algebra, right? You go and visit class 8 or 9 textbook, the sequence will always be the same. They start off with an expression, say for example x squared y, one variable expression xy, uh, x squared y, some variable, and then they will slightly move on to the from expressions they will move on to equations, and then from equations they will move on to functions. So here also we are doing the same thing. Now what do you mean by a Boolean function? Now a Boolean function is an expression formed by different binary variables. Obviously they will have the two binary operators, in fact three binary operators, AR operation, AND operation, and NOT operation, including the parenthesis and an equal to sign. So as an example, what is a Boolean expression is f1 equal to x, y, z bar is a Boolean function. Ideally, I should not have written this way. I should have written it this way, that is f1 as a function of x comma y comma z is equal to x, y, z bar. Right? What Boolean function says? Boolean function is an expression formed with binary variables. Yes, we have binary variables x, y, z. Then the two binary operators. Here we are having an AND operation here. Similarly, you can have an OR operation also. Say x, y, and an unary operator, right? Which is nothing but a NOT operator. We are having z bar here, and if required, you can put the parenthesis here, parenthesis, and an equal to sign. This is what is called as a Boolean function. So f1 is x, y, z bar. Another example we can give you is f2 is x plus y bar z, f3 is these functions, f4 is x, y bar plus x bar z. Now, when you create a truth table for this, how do you make a truth table for these functions? Your truth table, what are the variables here? The variables are x, y, and z. So which means that these are the input variables. These are the input variables, and input variables on the truth table on the leftmost side, you will have your input variables and its input combinations will be filled out here, right? So your input combinations will be there. Corresponding output functions will be towards the rightmost part of your truth table here. These are your output. I'll not write it as an output variable here, but I will be writing it as an output functions. Okay. So normally what we used to do is we will not write function. We will just write it as say z1 no z. What is the need for you to use this function is we used to write, say for example, a plus bc equal to z. A minus bc equal to x. So likewise, if we have n number of functions, you cannot keep on putting variables on your right hand side, right? That is the reason we are introducing these particular functions. So functions, it can be easily written as a function of variable x, y, z, and you can have any number of functions, something like this, f1, f2, f3, f4, not thinking about different variables to identify or represent these expressions. So here also you can prove here that f3 and f4 they are same, and the best way to prove is Obviously, by looking at these two expressions, F3 and F4, you cannot say that both the expressions are same, right? And the truth table is a more powerful media by which it will help you to see that F3 and F4 are same. If you create a truth table for this, then you will see that F3 and F4 are same. Now, there is a way to prove using algebraic manipulations also, which is slightly complex, but still, let me give you the proof. What is F3? F3 is x bar y bar z plus x bar y z plus x y bar. Now, from these two expressions, you can see that x bar and z are common. So, you pull out the common term, x bar z is common, multiplied by y plus y bar, plus the third term. Now you know that 1 plus y plus y bar is always equal to 1. So this will be 1. So it is equal to x bar z plus x y bar, which is nothing but your F4 expression. So on directly looking at the Boolean expressions, you cannot come to a conclusion whether two functions are equal. Your truth table will help you in identifying how the functions are really behaving. Okay. Now let's proceed further with the functions. Now please note we are looking at functions now. Now what is a complement of a function? Now if we write the function as f, then the complement of the function is f bar. Right. So please note that this is not a single variable. It may be a single variable function or it may be a multivariable functions also. Now, how do you obtain a complement of a function from a given function is change all ones to zeros and zeros to 1, you will get a complemented function. Very simple. That you are applying a duality equation here. So let us take an example here. If f1 is x, y, z bar, then what is the complement of this? Don't look down, the solution is there. So if I want f1 complement here, then I take a complement of the whole expression z bar, the whole bar. Right. Now I apply De Morgan's theorem. I break the bar, break the sign. So it becomes x bar, dot becomes plus, y becomes y bar, and z bar becomes, already see I'm interchangeably using this bar, so don't mind. So this bar and one more bar will be there. Complement of a complement. So this becomes x bar plus y bar. Complement of a complement is the same variable. So z. So now if you see what is our function, what is the complement of a function? If you change 1 to zeros and zeros to 1, you will get the output values, right? You will get the complement in fact. So let us look at the function here. We are creating a truth table for both f1 and f1 bar. X, Y, Z, all 7 possible combinations are here. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. For F1, it is X, Y, 0. That is, when F1 will be 1, when X and Y are 1 and Z is 0, you will have your F1 to be 1. When that will happen? It will happen when this is going to be 1, 1 and 0. So when it is 1, 1 and 0 here, your F1 will be 1. Now similarly, F1 bar. What is F1 bar? Either you can use this expression or you can use the complement also. But if you use this, then what is our objective here? Our objective is you change zeros to 1, you will get the complemented function, right? Let us use this particular, the last expression. That is when your F1 bar will be 1, whenever your X bar is 0 and Y bar is 0 and your Z bar is Z is 1, you will get F1 bar equal to 0. So F1 bar. You see here X is 0. Here also X is 0. So output is 1. Here also X is 0. Here also X is 0. The output is 1. Here Y is 0. So the output is 1. Y is 0. Output is 1. Here X is 1 here. So Y is 1. Z is 0. It is not satisfying this criteria. And the last one, Z is 1, so the output is 1. Right? Except this, all the possible outputs are 1. Now you compare the F1 column and F1 bar column. So as we defined in the function, you complement zeros to 1, you will get the complemented function. So you see 0 you complement, it becomes 1, 0 becomes 1, 0 becomes 1 likewise, and 1 becomes 0, 0 becomes 1. You have complemented all your functions, you are getting F1 bar function. Okay. So in this rule, what is the theorem that we applied? We just applied the De Morgan's theorem. X plus y plus z plus etc. the whole bar, you break the chain, right? It becomes x bar dot y bar dot z bar dot likewise. Similarly for the NAND operation, so x dot y dot z the whole bar can be written as x bar plus y bar plus z bar. So we applied the De Morgan's theorem here. Now, any doubt in the postulates? Any doubts in the postulates? Okay. Now let's move on to the gates, the more interesting part. Now, we have seen gates and or, NOT, XOR, NAND, right? So to start with, since NAND and NOR are the universal gates, let us try to implement these gates first. Because let us establish these NAND and NOR to be universal gates first. Now, what is a NAND operation? NAND operation means A dot B the whole bar. Okay. A dot B the whole bar. Similarly, NOR operation means A plus B the whole bar. And this bar has come because of this bubble. Similarly, this bar has become because of this bubble. This is nothing but we can say that this is a bubbled AND. This is a bubbled AND. This is a bubbled OR. No, I should not say bubbled AND. I should say AND bubbled. Similarly, here NOR and bubbled. See, there is a difference. If I say bubbled AND, it means that my inputs are bubbled and then it is an AND operation. And here I am saying that it is AND bubbled, NOR bubbled. Okay. Now, let's look at the truth table XOR gate. Right. So XOR, it is nothing but an exclusive OR, meaning that whenever the inputs are same, your output will be 0. Whenever the inputs are different, your output is 1. So what is the gate symbol? Gate symbol is you have an OR and then you have one more OR, which is nothing but XOR, right? Which is nothing but XOR. What is the expression for XOR? A XOR B is A bar B plus A B bar. And how did you get this? How did you get this expression? You got this expression from the truth table only. How? Okay. So the input combinations of A and B are 0, 0, 0, 1, 1, 0 and 1, 1. What is the XOR gate's output? Whenever both the inputs are same, your output will be 0, right? So your output is 0. Whenever the inputs are different, your output is 1. Now, look at the output column for XOR gate. When is this A XOR B, which is nothing but your output variable, is 1, it is 1 here and it is 1 here. And this 1 corresponds to 0 and 1, which means that you got this one because of 0 and 1 and you got this one because of 1 and 0. What is 0 for A correspond to? This we can write it as A bar, because in the variable input A bar means it is 0. Similarly, B corresponds to B. 1 corresponds to B, sorry. Similarly, here 1, 0 here, this corresponds to A and this corresponds to B bar. So, an OR operation of this two functions is nothing but A bar B plus AB bar is what is your XOR gate output is. Okay. Similarly, an XNOR gate output. We know that this is the symbol of an XNOR gate. XNOR gate truth table is whenever both the inputs are same, you will have 1, else it is 0. So this 1 corresponds to what? It is A bar, B bar. This one corresponds to A, B. So the OR operation of this A bar B plus AB is what is the NOR operations expression. A bar B bar plus AB. Right? Now let's move on to the function implementation. Now I have a function f1 equal to Now I have a function f1 equal to x plus y bar z. Okay. Now how do I implement this using gates? How do I implement using gates is first, what are my variables? I have x, I have y, and I have z. These are the 3 input variables. Now x, now before that, you know that the complement gets the precedence before the existing rule, right? So what is the complement of, first we must draw the complement of y. So the complement of y is y. So we got y bar. And then what takes precedence? Y bar z will take precedence. So the AND operation of this is nothing but y bar z. Then the OR operation will take precedence. So the OR operation of this. So here it is x plus y bar z, and this is what is your function f1 is. Okay. So this is how we implement the function using gates. Okay, so this is how we implement the function using gates. Similarly, let us implement the 2 functions that we just saw. What are the 2 functions we just saw? We saw for an XOR gate. Yeah. So it is, let us take another function. Say for example, x y bar plus x bar z. These are 2 functions. First, you list down all the input variables. We have x, we have y, and we have z. So first we need the complement of x. So we need the complement of x. This is x bar. And then we need the complement of y also, right? So we are having the complement of y. So it is y bar. Now first let us implement this one, x bar z. So I have x bar here and z is here, and of this. Okay. X y bar. So I have x here and y bar, let me take somewhere here, and then the AND of this. So what is this? This is x bar y, and this one is x bar z, and the OR operation of this will be, if I represent this function to be f2, and this is the function f2 output. Okay, I hope now you understand how do we do a gate implementation of different functions, right? So I think it's time we will continue the gate part. We have entered to an interesting part now. So I think we are going to play around with gates now from next class. It will be more interesting now. Any doubts so far? Any doubts?